Hello everyone. Let's solve example 6 from lecture 2. Here we have to apply transformation technique to get the PDF of y from PDF of x. And PDF of x is given here. That's equal to, so PDF of x is equal to 4 times x cubed if x is in between 0 and 1 and 0 if otherwise. And the second thing that we know is y is actually equal to minus ln x to the power 4, which is the same thing as ln x to the power minus 4, right? Now we are searching for fx, so f y of y and capital F y of y. Okay. First thing to do is we have to get the inverse function g minus 1 of y, and to do that we know that y is equal to ln x to the power minus 4. That implies that if you exponentiate both sides, e to the power y is equal to x to the power minus 4, which implies that x is equal to e to the power minus 0.25 y. Okay, let's put that into a box. Now let's move on. The second thing that we need is we have to evaluate the derivative of this inverse function. So evaluate the derivative of this inverse function with respect to y and take the absolute value. If you do that, this is going to give you minus 0.25 e to the power minus 0.25 y, obviously, and once you take the absolute value, that gives you 0.25 e to the power minus 0.25 y. Okay, so let's put that into another box. Okay, this is the derivative, the absolute value of the derivative. Now, third thing that we need is we have to evaluate, so fx at the inverse function, which is easy. We know that f of x is equal to 4x cubed. Instead of x, we are going to plug the inverse function, and inverse function is here, right? So 4 times e to the power minus 0.25 y, and we take the cube. That gives us 4 times e to the power minus 0.75 y, okay? And finally, we can get a PDF of y. So PDF of y is basically the second term multiplied by the third term, right? So it's basically equal to 4 times, let's take the third term first, 4 times e to the power minus 0.75 y times 0.25 times e to the power minus 0.25 y. And if you multiply them together, you receive e to the power minus y. Okay, so this is the PDF of y. Now let's have a look at at the boundaries of this. Indeed, this is the case, so we can rewrite it in this way. We have to say that f y over y is equal to e to the power minus y, then y goes from 0 to positive infinity. Why? Because look at the boundaries here. Look at the boundaries here. So x gets the value of 0, the low bound of x is 0 and upper bound is 1. When you are plugging it into this function, so when x gets value of 0, in that case you're going to receive positive infinity here. And once you plug 1, ln 1 is obviously 0. So basically when x goes from 0 to 1, when it varies between 0 and 1, then y is going to vary between 0 and positive infinity, right? And then 0 if otherwise. So that is the probability density function of y. Okay, now what we have to do is we have to receive the CDF on y. Okay, CDF on y is a question mark. So we can do it in two ways actually. First thing, we know that f y just a second. We know that y of y is nothing but the integral of the PDF of y. Let me use PDF of y up to y, right? This is how you get the CDF from PDF. So given the PDF of y, we can say that y equals to probability that random variable y is less than or equal to y, and that is equal to, so what is the PDF of y? PDF of y is equal to e to power minus y. So we say e to power minus y minus t. We replace y with t because we're going to send it from minus infinity to some y dt. So if you do that, if you take the integral, that gives you minus e to power minus t, and then you have to evaluate it from minus infinity to y. But here, pay attention to one fact, that PDF is varying between 0 and positive infinity. So actually we have to, instead of minus infinity, we have to evaluate it between 0 and y. So maybe you can also do it in this way. I mean, you can just say that we are, because PDF varies between 0 and positive infinity, PDF is non-zero between 0 and positive infinity, just integrate from 0. Okay, now once you do that, you get this integral, right? And if you evaluate it at y, you're going to receive e to power minus y minus, and now if you evaluate the integral at the lower bound, you're going to receive minus e to power minus 0. That gives you 1. So you get positive 1 minus e to power minus y. And that is the CDF. So we can say that the CDF of y is nothing but 1 minus e to power minus y, given y is in between 0 and positive infinity, and 0 elsewhere. Okay, that is one way. The second way is, if you know the CDF of x, so let's call it CDF to CDF method. So what I mean is, if you know the CDF of x, you can easily map it to CDF of y. Okay, now let's talk about this method. For that, you have to know the CDF of CDF of x. Now let's see whether we can get the CDF of x from this PDF. We know that the PDF of x is 4x cubed when x is in between 0 and 1. So fxx is actually equal to, so from 0 to some x, 4 times x cubed, 4 times t cubed dt. And if you evaluate that integral, that gives you 4 times t to power 4 divided by 4, which is just t to power 4. You have to evaluate it within 0 and x interval, and that is going to give you x to power 4, right? So after that, once you know the CDF of x, you can easily map it to CDF of y. How you do that? So we are searching for CDF of y. That is obviously equal to probability of y less than or equal to some y, fixed value y, right? So now we can, map y to x. We know that there is a map between x and y. So x is indeed equal to, x is equal to what? Here it is, e to power minus 0.25y. So let's replace it with that. So that is equal to probability e to power minus 0.25y, capital Y obviously. Sorry, I made a mistake here. So instead of y, we have to plug the x, and so x is equal to, so y is equal to minus ln x to power 4. Just plug minus ln x to power 4 less than or equal to some y. right? If that is the case, what we can do is we can say that, maybe to be more clear, we can say that this is nothing but ln x to the power minus 4 being less than or equal to y. That is the same thing as ln 1 over x to the power 4 being less than or equal to y, which is the same thing as, if you exponentiate both sides, you're going to receive probability 1 over x to the power 4 is less than or equal to e to the power y. But now we want to switch, numerator and denominator. And once you do that, we have to be careful. We have to switch the inequality sign. So this is the same thing as probability x to the power 4 is greater than or equal to 1 over e to the power y, right? And that gives you probability of x being greater than or equal to e to the power, so 1 over e to the power, it's, we are taking 1 over 4 y, right? So we said that, look at this, probability of x being greater than or equal to 1 over 0.25y, right? So probability x being greater than or equal to 1 over e to the power 0.25y, isn't it? And we can rewrite it as probability of x being greater than or equal to e to the power minus 0.25y. And we know that, look at this, we can basically switch the inequality. Suppose you have, this is some fixed value. So this is the CDF of x, PDF of x actually. So if you are interested in the area greater than a fixed value, e to the power minus 0.25y, so this is, let's call it a, and the non-shaded area is b. So obviously, a can be found as 1 minus b. We use this same relationship and we say that this is the same thing as 1 minus probability of x being less than or equal to e to the power minus 0.25y. And now we already know the CDF of x, so therefore we can evaluate the CDF of x. So instead of this, we plug the CDF of x, evaluate it at this value. Okay, so this is f of x evaluated at e minus 0.25y. And let's have a look at the CDF of x. What is CDF of x? CDF of x is here. So it's basically x to the power 4. Maybe I have to use red color. So it's basically x to the power 4, right? And obviously this is the case when x varies between 0 and 1. So now evaluate this thing at, evaluate CDF of x at this particular fixed value that is going to be equal to 1 minus e to the power 0.25y, and we're going to raise it to exponent 4 because the f of x is x to the power 4, right? So instead of x, we plugged e to the power minus 0.25y and then exponentiated. That gives you 1 minus e to the power minus y. That is exactly the same solution. This is a y. So you can see that this is exactly the same thing as what we received here. See? So we have basically two techniques. When you know the CDF of x, you can basically map it to CDF of y. It's easy. And you can obviously, do both methods. Transformation method is useful when you know PDF of x and you want to get PDF of y. But you can still do it in this way. You can, if you have PDF of x, you can find CDF of x, and from CDF. So you can go in multiple ways actually. So if you are given the PDF of x, what you can do is you can basically find the CDF of x. Then from that you can map it by using the CDF to CDF method. You can find the Fy of y, and from that you can get lowercase, so PDF of y, right? Because we know that PDF is nothing but the derivative of the CDF, right? That is another approach. Now let's have a look at the next question. Example 7. In example 7, we have a little bit trick here. You see here, this function, the map of x to y, is not monotonic in the sense that x squared is increasing at some point, at some interval, and decreasing at some interval. Therefore, there are actually multiple values of x that corresponds to a single value of y. So this inverse function is not global in this case. Therefore, it is a little bit tricky. So now let's look at that, how we can solve it. So let's rewrite it. We said that the CDF of x is equal to 0 if x is less than 0. It's equal to x squared if x is in between x and 1, and to 1 if x is greater than 1, greater than or equal to 1. Now the question is, and we know that y is equal to x squared. So the question is, find the CDF on y. So here, obviously, because we have CDF of x, we can use the CDF to CDF method. So how we do? We proceed in this way. We are interested in, let me use blue color for the solution. So we are interested in Fy of y. That is the same thing as probability of y being less than or equal to a particular y. And we know that y can be replaced by x. So this is the same thing as x squared being less than or equal to y. And here we have to be careful because this probability corresponds to probability of x being in interval between minus square root of y and positive square root of y. The reason for that is this. Suppose you have function. This is x, and here you have x squared, right? Let me use another color. So you have x here, x squared in the y-axis. Suppose you have y equals to 1, and obviously when you say x squared is less than y, less than 1, that corresponds to values of x less than negative 1, greater than negative 1, and less than positive 1. Okay, so therefore this probability corresponds to the probability x squared less than y corresponds to the probability that x falls within this interval. Now let's continue. So we know that there is a theorem telling that this probability can be found by evaluating the CDF of y at the same as CDF of x. So evaluating the CDF of x at here actually, because we're talking about the random variable x, we have to use the CDF of x, not y. So we have to evaluate CDF of x at positive square root of y minus the CDF evaluated at minus square root of y. Okay, now let's do that. So what is the CDF of x? CDF of x is basically equal to x squared. Whenever it's between 0 and 1, whenever x is between 0 and 1, the CDF is equal to x squared. So when we are taking the positive value, we have to say that we have to evaluate it as x squared. So instead of x, we plug square root of y and just square it. Minus, now let's have a look at this. When x is negative, when x is less than 0, negative, it's always equal to 0. So we just say that when you are evaluating the CDF of x at negative value, this gives you 0. So in the end, you receive y. Yes, so this is the solution. And here you have to say that fy of y is equal to y itself if, once x is varying between 0 and 1, right, then x squared is also going to vary between 0 and 1, and it's going to be equal to, if x is greater than 1, then y is going to be greater than 1, obviously. So y is greater than or equal to 1, and 0 elsewhere. And 0 elsewhere. Okay, great. What else we can do? We can get the same solution in the other way. So we can get the PDF of x, right, from the CDF. Obviously, we have the CDF of x, and then from PDF of x, we can use the transformation method and get the PDF of x directly, right? Yeah, here what we miss is, yes, let's derive the PDF of y. So PDF of y, so let me rewrite it. Fy of y is equal to 0 if y is less than 0. It's equal to y itself if y is in between 0 and 1, and equal to 1 if y is greater than or equal to 1. If this is the case, then I can say that fy of y is equal to derivative of CDF, and that is going to be equal to what? This is going to be equal to 0 if y is less than 0. Actually, I should say that, I should put it in this way. I should say it's equal to 1 if y is in between 0 and 1, and 0 if else. Right? This is the probability density function for y, and that means that this is uniform distributed. So what else we can do is, if you want, there is another technique to get the PDF of y from. We could do it in this way. So from CDF of x, which is given to us, we get PDF of x by taking derivative, and then we use transformation method to get fy of y. Okay, this is how we can go. So obviously, if fx is equal to 2x squared, then PDF of x is going to be equal to derivative of this, so it's going to be equal to 2x if x is in between 0 and 1, and 0 if else. Right, we just took the derivative of x squared. Yes, the CDF of x is x squared, and if you take the derivative, it's 0 everywhere except for 0, 1 interval. When it's 0 and when the x falls within 0, 1 interval, the PDF is just the derivative is just 2x. Then after you get it, you can use the transformation method. We know that f(y) of y is equal to fx evaluated at the inverse function times the derivative of the inverse function, the absolute value of the derivative of the inverse function with respect to y. Now let's plug for this, guys. So we know that y is equal to x squared, right? So inverse function is inverse function here is x is equal to plus minus square root of y, right? This is the inverse function. But here you have to keep in mind that, by definition, x cannot receive negative value. I mean, when x receives negative values, then its CDF is equal to 0. You can have a look here. See, when x is negative, the PDF and CDF, they are both 0. So therefore, we are just taking the positive solution, positive part of the PDF. So we say that this is equal to, let me say that this is equal to 2 times, so 2 times x. Instead of x, I'm plugging the inverse function, which is square root of y times, if you take the derivative of the inverse function with respect to y, you're going to receive 0.5 divided by square root of y. And that gives you 1. If, obviously, this happens if y is in between 0 and 1, and 0 if else. Okay, you see, here we used several techniques to get the PDF of y. So that is all for transformations. So basically we cover 2 methods, CDF to CDF method and transformation method, or you can call PDF to PDF method. And you can use various combination of these rules to get PDFs and CDFs of a variable from PDFs and CDFs of another variable. That is the essence. Now what else? So here we talked about expectations. Yeah. Example 8. Example 8. Example 8 is asking you to find what? Expectation of x, where x is the number of points from throwing a single dice. So for that, we know that, when you have discrete random variable, then expectation of x is nothing but each value of the random variable x times probability that random variable x takes that specific value. So for this, we have to find the probability mass function. You know that probability mass function is the same thing as the single point probabilities in discrete case. So probability mass function in dice rolling experiment is equal to 1 over 6 when x equals to 1, 2, up to 6, right? And 0 if otherwise, isn't it? Now, if you want to find the expectation of x, use this formula. Let me put the formula under the within the red box. So this is going to be equal to each value of x, so 1 times 1 over 6 plus 2 times the probability that x equals to 2, that is 1 over 6, plus 3 times 1 over 6 plus 4 times 1 over 6 plus 5 times 1 over 6 plus 6 times 1 over 6. And that is going to give you 3.5. That is the essence. Now let's look at example 9. We have a probability density function of a continuous random variable that is equal to 4x cubed, and we have to find expectation of x and expectation of x squared. So example 9, we know that is equal to 4x cubed when x is in between 0, 1 and 0 else, if else, right? So expectation of x is, in continuous cases, is actually the integral from minus infinity to positive infinity of x times fx of x dx, right? And here actually we know that the PDF is equal to 0 everywhere except for 0, 1 interval. So we can say that I'm going to integrate between 0 and 1 x times f of x, which is 4 times x cubed dx, and that is going to give me 4x to the power 4 integrated between 0, 1 interval. And that is, if I integrate out, that gives me x to the power 5 over 5, right? And if I evaluate it within 0, 1 interval, that gives me 4 over 5. That is the solution. Now, if I want to find the expectation of another function, expectation of x squared, I do the same thing. That is basically integral from minus infinity to positive infinity x squared times fx of x dx. Now, I know that fx is 0 everywhere except for 0, 1 interval. So I just integrate between 0 and 1 x squared times 4 times x cubed dx. That gives me 4x to the power 5 integrated between 0 and 1, right? Square. So that gives me 4 times x to the power 6 over 6 evaluated within 0, 1 interval, and that gives me 4 over 6, and that is the solution. Okay, maybe I have to put them on the within the box. So this is one of the answers, and this is, let me use another column. So this is the solution to the second question. What else? Example 10, we have to take we have to find expectation of x given, you know, given this PDF. So example 10. Oh, let's do that. Example 10. So we're given the fx of x, which is equal to 1 over x squared if x is between 0 and 1, and 0 if otherwise. Let me see whether I copied it correctly. Yes. Oh, I'm sorry, this should be 1 over x squared within. So when x goes from 1 to positive infinity and 0 elsewhere. So I made a mistake here. So if x goes from 1 to positive infinity, 1 to positive infinity, and 0 if otherwise. Now expectation of x is the quantity that we are searching for. Let me use another color for the solution. Expectation of x is going to be equal to integral of x from minus infinity to positive infinity, x times fx of x. We know this. And here we know that PDF is 0 everywhere except for 1 to positive infinity interval. So I just integrate within this interval x times 1 over x squared dx. That is the same thing as integral from 1 to positive infinity of 1 over x dx. And then that gives me what? If I take the ln of x, that is the integral of, if I integrate out, I get ln of x, and I have to evaluate it within 1 to positive infinity, right? And in this case, I guess there is some kind of mistake here, because if I take the log of x. If x is evaluated at positive infinity, you're going to receive positive infinity. So here probably there was some kind of mistake. Let me recheck it. Yeah, so in this particular case, the solution is positive infinity. In this case, we say that the expectation does not really exist because, yeah, so the expectation does not really exist because if you are evaluating ln of x at positive infinity, you get positive infinity, and if you evaluate it at 1, you're going to receive 0, so the result is positive infinity. So you say that expectation of x does not exist. This is how you write it. Okay. Now we have several facts about expectation. So you have the constant, expectation of constant is constant itself, and so on and so forth. Now let's move to next questions. So example 11, we have to find first two row moments through moment generating functions. Okay, so moment generating function is, it's basically the expectation of e to power tx. T is some constant, some positive constant. Okay, and you are finding this expectation, and then after you set the moment generating function value at if you take the derivative, you see the first derivative of the moment generating function, if evaluated at 0, gives you the expectation of x. You see, so let's see how we can derive it. Let's see how we can derive it. So let me rewrite it. This is example 11. Here we are given fx of x, which is equal to e to power minus x if x runs within 0 and positive infinity, and 0 if otherwise. Okay, so we have to find mxt first, and then we have to find, using the moment generating function, we have to find the first row moment. So first row moment means the expectation of x to power 1. The second row moment means expectation of x to power 2, and so on and so forth. So rth, if you are interested in the rth row moment, that is expectation of x to power r. Okay, so these are the things that we are searching for. Now first, to get the moment generating function, this is exactly equal to e to power tx. This is basically the expectation of e to power tx. And we know that to find the expectation of any function, you just put it under the integral sign, copy the function itself, multiply by the probability density function, and integrate it. So this is the same thing as, look at the boundaries. Here we see that the boundary of this PDF, so PDF is non-zero only within 0 and positive infinity interval. So basically when you have negative values of x, PDF is equal to 0. Therefore we just change the interval in this way. And here we get e to power t minus 1 times x. Okay, dx. So in that case, if you basically integrate this, you're gonna receive what? You're gonna receive e to power t minus 1 times x over t minus 1, right? And you have to evaluate it within this interval. So keep in mind that t should be negative. T should be less than 1, actually, not negative, but less than 1. It's positive, but it should be actually, let me use red color. If t is not within this interval, then this integral is not going to be evaluated. It's not going to exist actually. Why? Because when you are plugging positive infinity for x, e to power positive infinity is basically positive infinity, given that t is greater than 1. Therefore, to make sure that this moment generating function exists, t should be between 0 and 1, okay? So plug the positive infinity here, t minus 1, given that this is a negative value, times positive infinity. Let me use quotation marks because this is not a correct way of doing it. It's mathematically not correct. Minus e to power t minus 1 times 0, and I'm dividing both sides by t minus 1. So as a result, what will happen? Suppose this is negative infinity. So suppose t is less than 1, then you receive e to power negative infinity, right? Divide by t minus 1 minus e to power 0 divided by t minus 1. And as a result, you receive, this guy cancels. Let me use another color here. This guy cancels out. This is 0. And then you receive minus 1 over t minus 1, which can be rewritten as, given t is less than 1, you can rewrite it as 1 over 1 minus t. So this is the moment generating function of x. Remember that. So let me use red color. So what else? So we want to find the expectation of x, the first row moment. This is called first row moment, and second row moment of x using the moment generating function. Now let's continue this example. What we can do is we can go in this way. We know the moment generating function of x. Let me use black color. We know the moment generating function of x. This is equal to 1 over t minus 1. And we know that by theorem, expectation of the first row moment is actually can actually be found. You know, x to power 1 is just x. So you can find it in this way. You just take the first derivative, you see. Just take the derivative once of this function, and then evaluate the derivative at t equals to 0. So we know that if you take the derivative of this is going to be equal to, I'm sorry, I made a mistake here. It's actually 1 minus t, 1 over 1 minus t. This is the moment generating function. Let me put it into the red box. Okay, so if you are taking the derivative of this thing, you're going to receive, you're definitely going to receive 1 minus t to power minus 2, right? Because it's 1 minus t to power minus 1. So if you are taking the derivative, the first derivative of this moment generating function is going to give you 1 minus t to power minus 2. And if you are evaluating it at t equals to 0, that is going to give you 1. Okay. Now, if you want to find the second row moment, meaning expectation of x to power 2, that is the second row moment, using the moment generating function, then you have to take the second derivative for the moment generating function and then set t equal to 0. Now we have already taken the first derivative, and the first derivative is equal to 1 minus t to power minus 2. And we know that if you take the second derivative, it is going to be equal to what? It's going to be equal to minus 2 times 1 minus t to power minus 3 and times minus 1, right? And you have to evaluate it at t equals to 0 again. So here, if you simplify, you're going to receive 2 times 1 minus 0 to power minus 3. You know, we set t equal to 0, right? So that is going to give you what? That is going to give you 2. And that is the second row moment So you can try this. If you want, you can recheck your solution. Look, this is the probability density function. Obviously, we can. You see here the difficulty is that you have to use the integration by parts. I believe. So you can find, if you want to recheck it, you can use the PDF method to get the expectation of x. That is basically x times fx, which is e to power minus x dx, evaluated within 0 to positive infinity. So for that you have to use integral by parts, and that is a long story. Okay, so that is example 11. What else do we have here? Nothing. Okay, now let's solve example 12. How many elements are there in the sample space if you are tossing fair coin 4 times? Now, here you have 4 empty boxes, and in each empty box you have 2 possibilities. 2 possibilities going into each empty box. Here we have replacement and order. Therefore, the total number of elements in your sample space is going to be 2 to power 4. And the cardinality of sample space is actually equal to 16, to 2 power 4, right? Now, in B part of example 12, we're asked to find the probability mass function. Here, it's a little bit tricky. I was looking for a combinatorics formula, but I could not find, at least. I guess there is no such formula that can be applied in this case. So first we start with the, we are interested in how many times tail is followed by head. The maximum value of this random variable is actually 2, and there is only one specific case. You see one case corresponding to this particular outcome. TH. So the first trial you get tail and then head, tail, head. So here tail is followed by head 2 times. Now let's look at this second case when x is equal to 0. I listed all those cases. There are 5 cases. So in all of those 5 cases, there is actually no follow of tail by head. And in total, we have 16 outcomes. It means that one follow can be, the cardinality of the event that, head follows tail only once is equal to 10, because in total we have 16 cases, 16 elements in the sample space. 16 minus 5 minus 1 gives you 10. Yes, because we have one case corresponding to event, let's say A. This is event, let's say this is event A1, this is A2. So if A1 and A2 contain 6 elements in total, it means that A3 should contain 10 elements, So that is kind of an easy workaround for this problem. Okay, so the probability mass function is going to look like this. So 5 over 16 if x is equal to 0, so no follow. Then 10 over 16 if follow is 1, and 1 over 16 if there are 2 follows. Now to find the expectation of x, random variable x, this is, discrete case, they have to use this formula. X times the value of probability mass function, corresponding the value of probability mass function, and if you do that, you receive 12 over 16 as the expectation. As for variance, you know that this is the formula for variance. So you basically subtract the expectation from each value of x, square that, and then multiply by the corresponding value of probability mass function. As a result, we receive 0.31. Now in D part, we're asked to find the moment generating function. We know that moment generating function is nothing but the expectation of e to power tx. so the expectation of this function. And to find the expectation of this function, we know that in discrete case we multiply the function by we evaluate function at each value of x and multiply by the corresponding value of probability mass function at the particular x. Okay, so we do that, we receive something like this. So this is the if you do that, so first value of x is equal to 0, e to power 0 times x gives us 0 times the probability of 0 is 5/16. The second value of x is 1, so e to power 1 times t. We are evaluating the e to power tx function at x equals to 1. Probability of that particular value is 10/16 plus e to power 2t times 1/16. These guys are 16s. Yeah? Let me use black color. 16. So as a result, you receive the moment generating function. And if you want to find the expectation of x, this is, I guess, in the e part. So what you have to do is you have to so the first row moment is expectation of x to power 1, which is the same thing as expectation of x. For that, you have to take the derivative of moment generating function, the first derivative, because you are interested in the first row moment, and set t equals to 0. And if you do that, what you're going to receive is, you see, the derivative of this is going to be equal to 10 e to power t over 16 plus 2 e to power 2t over 16. And if you evaluate it at t equals to 0, you receive 12/16, which is exactly the same thing that we have received for expectation here, you see. Now, as for variance, what we have to do is we have to take the second derivative of the moment generating function, because the variance is this second row moment. Actually, here we have to be careful. So you see the variance of x, actually it's not the second row moment, this is second central moment. Variance of x is equal to expectation of x squared minus expectation of x then squared. These are two different things. This formula is given in the lecture notes. So we know this guy is equal to 10/12, actually 12/16, I'm sorry. This guy is equal to 12/16. We have already found that. Now, this is the second row moment. To get this second row moment, we can use this trick. So you are taking the second derivative of the moment generating function and then setting t equal to 0. So that is the same thing as, let me look at that. So the first derivative is 10 times e to power t over 16. So we're basically taking the derivative of this function, 10 e to power t plus 2 e to power 2t and everything over 16, right? I guess I copied correctly. And then what you have to do is you have to get it and then evaluate it at t equals to 0. Okay, now let's take the derivative. 10 times e to power t, if you take the derivative, that gives you 10 e to power t over 16 plus if you take the derivative of the second term, you're going to receive 4 e to power 2t divided by 16. And if you evaluate it at t equals to 0, you're going to receive 10 e to power 0 plus 4 e to power 0 divided by 16, which is equal to 14/16. So let me check it. So 14/16. So now this means that, so this is nothing but expectation of x square. Let's put it under the within the box. So it means the variance of x. So variance of x is going to be equal to expectation of x squared, which is 14 over 16, minus the expectation of x, 12 over 16 squared. And if you calculate that, let me calculate it using calculator. So 14 over 16 minus 12 over 16 squared, and that gives us exactly the value that we have already found. We can try that. Okay, so this is the solution that we have already obtained using the probability mass function method, the norm method. So what? Let's see. Okay, we have inequalities, some famous inequalities that Markov's inequality, which tells us that here we have to be careful, because here the function gx should be non-negative. It should be non-negative. If that is the case, then expectation of we say that the probability that gx is greater than some positive constant c is actually going to be less than or equal to expectation of gx over c. And that actually follows, this actually leads to Chebyshev's inequality. There is a famous derivation of it. I don't want to repeat it. The second thing is Chebyshev's inequality. It has actually three forms. You have to be careful with these three forms. And then you have Jensen's inequality. If you have a convex function, and if you have x, which is a random variable, in that case, the function of expectation should always be less than or equal to expectation of the function. Okay. Now let's look at the example 13. So we have to use Chebyshev's inequality to find upper bound to the probability that a random variable deviates from more than 3 standard deviations from its mean. It's very easy. So instead of k here, we are going to plug 3. Okay. Look, we're going to use this part for example 13. So probability that x minus mu is greater than 3 sigma. That is obviously going to be less than 1 over 9, because k is 3 in our case. Okay. And that is upper bound, because that probability is going to be less than or equal to 1 over 9. So let me rewrite it here. So example 13, we're interested in probability that x minus mu is greater than or equal to 3 standard deviations. So basically, random variable x deviates from its mean by more than 3 standard deviations. By Chebyshev's inequality, this is always less than or equal to 1 over 3 squared, which is equal to 1 over 9. And that is the solution. Example 14, we have a PDF. Okay. Let me solve it here. So we have a PDF, and we have to evaluate this probability that x is absolute value of x is greater than 15. So we have to use exact. If we have to find exact probability using probability density function, also we have to use Chebyshev's inequality for that. Now, let me write it here. Example 14. What is that? So this PDF is 1 over 2 times square root of 3. If x is in between minus square root of 3 and positive square root of 3, I guess. Right? And 0 elsewhere. 0 else. So we have to evaluate this probability that this x is greater than 1.5. Okay. So here we have to have x, absolute value of x greater than 1.5, we have either x being less than minus 1.5 or x being greater than 1.5. So there are two cases. Either x is less than I'm sorry, either x is, so here we have x is less than or equal to minus 1.5, or x is greater than or equal to 1.5. So in both cases, this thing is going to work. We can, but it's easier to do it in this way. We can say that using the rule of complements, we can say that this probability is the same thing as probability of absolute value of x being less than 1.5, obviously. And this is the same thing as to say that probability that x is in between minus and positive 1.5. And this probability can be easily calculated using the probability density function. So we're going to calculate it as 1 minus integrate between minus 1.5 and positive 1.5 the probability density function, and that gives you what? 1 minus 1 over 2 square root of 3x, and here we have to evaluate it in between minus 1.5 and positive 1.5, and that is going to give you 1 minus 1 over 2 square root of 3 times 1.5 plus actually minus, because you have minus here and minus in the beginning, so maybe it's better if I write it in this way. So minus 1.5 over 2 square root of 3, so that gives you 1 minus 3 over 2 square root of 3, which is equal to what? And that is approximately equal to 0.13. Okay, that is the exact probability. Now we are asked to find the Chebyshev bound, I mean the upper the boundaries using the Chebyshev's inequality. So for that, remember, for Chebyshev's inequality, you have to find the mean and variance of the random variable. So first, let's find the mean of the random variable. So expectation of x is nothing but, we know that in continuous case, so these are the boundaries where PDF is not equal to 0. So we have to integrate it. Right? Integrate x times the PDF, which is 1 over 2 times square root of 3 dx. And if you do that, you're going to receive x squared over 2 times square root of 3 and 2 times 2, and evaluate it at this interval. And if you do that, you receive what? You receive 3 over 4 square root of 3 minus, and then minus 3 over 4 square root of 3. In the end, you receive 6 over 4 square root of 3, right? So I think I made a mistake. Just a second, because once you plug it here, okay, I got a mistake here. It should be positive, because once you square it, you're gonna receive a positive value. So it's gonna be equal to 0, exactly 0. So did I have the same mistake? I don't know. Here we don't have squaring. No, it's correct. So yeah, so the expectation of x is equal to 0. Now let's find the variance. And to find the variance of x, we know that it's equal to expectation of x squared minus expectation of x and everything squared, right? So we know this guy, this is equal to 0. So we can say that this is exactly equal to expectation of x squared in this particular case. And what is expectation of x squared? This is basically equal to integral from minus square root of 3 up to positive square root of 3. X squared times 1 over 2 square root of 3 dx, which is equal to x cubed over 3 times 2 square root of 3 evaluated within this interval. And that is going to give you square root of 3 cubed minus square root of 3 cubed, and everything divided by 6 times square root of 3. And as a result, we're going to receive what? We're going to receive so we can rewrite it as 2 times square root of 3 to power 3 over 6 times square root of 3, and that gives you 1 over 3 times 3, isn't it? Because you cancel out these things, this and this thing cancels out, and you receive just 3. And as a result, the variance becomes equal to 1. So the variance is equal to 1. Great. Now we have to use Chebyshev inequality to evaluate, to find the boundaries of this probability. Probability x is, absolute value of x is greater than 1.5. So let's use another new page. So probability. So we are trying to find the upper bound of this probability. X is greater than or equal to, just a second, X is greater than 1.5. Okay, for that we have to use Chebyshev's inequality. Let's see which one makes sense for us. So whenever x minus mu is greater than something, so the upper bound is 1 over k squared. Okay, so again the same inequality is going to be used. Just a second. So we know that the expectation of x is equal to, we found that this is equal to 0. Expectation of x is equal to 0 here, and the variance is equal to 1. So we can rewrite it in this way. We can say that this is the same thing as probability x minus 0 mu greater than or equal to 1.5 times sigma, which is just 1. So by definition, this should be less than or equal to 1 over k squared, and k here is 1 over 1.5 squared, and that is equal to what? So if you divide 1 by 1 over 1.5 squared, that gives you 0.44. So at most, this probability is going to be equal to 0.44, which is correct actually, because the exact probability is 0.13, and the upper bound for this, the maximum value of this probability is equal to 0.44 by Chebyshev's inequality. Remember, the Chebyshev's inequality tells you that probability that x deviates from the mean, from its mean by more than some k standard deviations, is always less than or equal to 1 over k squared. Here we got a nice expectation. The mean was equal to 0, so we just plugged for the mean, and the variance was also good because it was equal to 1. So instead of sigma we plugged 1, and it means that our k is equal to 1.5, and then we find that this probability in total is less than 1 over k squared, or 1 over 2.25, which is equal to 0.44. So that is how you bound the probabilities using the Chebyshev's inequality. Let's see what else we have here. Okay, we have independent random variables, and each of them have the same mean. So actually we have Bernoulli distribution. Each x is Bernoulli distributed. The mean is p. Variance is p times 1 minus p for all of them. This is called IID distribution, identically and independently distributed. And then we have the sample mean. We have to find the expectation of x bar n and variance of the sample mean. And then we have to find the minimum n such that this probability is greater than 0.9. Okay, let's solve the part A first. So this is example what? Example 15. So you have a sequence of random variables up to xn, where xi is Bernoulli with probability of success equal to p. Now what we have to do is x bar n is equal to summation of xi. I goes from 1 to n, divide by n. So if this is the case, find expectation of x, and expectation of x bar n and variance of x bar n. So for that, the expectation of x bar n is equal to the expectation. Let's plug the definition of x bar n. X bar n is nothing but summation of xi, I goes from 1 to n, divided by n. And we know that expectation is a linear operator, meaning that when you have additive function, you can apply to each element separately. So this is the same thing. You can basically interchange the summation and expectation due to the properties of the expectation. Expectation of xi, I goes from 1 to n over n. And we know that expectation of xi, each xi is just equal to probability of success p. So we can say that it's equal to n times p. We have n such x's, and each x has expectation equal to p. So divide by n. In the end, you receive p. Okay. So expectation of x bar n, the sample mean is going to be equal to p. Okay. Now let's find the variance of x bar n. We know that this is going to be equal to expectation of, x bar n squared minus expectation of x bar n squared. But we can use another trick here, I believe. So because you have independent and identical distribution, you can say that. So let's use the property of the variance. You can rewrite it as variance of, let's plug for x bar n. The definition of x bar n is xi, I goes from 1 to n, divided by n, right? So you can apply variance into each of these, onto each element of this summation. And you don't have, you have independence assumption here. So you can rewrite it as, because of independence, you don't need to take into account covariances. Here it is going to be equal to sum of variance of xi's over, but remember one fact. If you remember, let me state that fact, general fact. So if you have variance of a times x, a is a constant, this is equal to a squared times variance of x, right? We know it. Now let's apply this particular property of the variance. So here, maybe I should say that I can easily write it because of the property of the variance, and as long as n is a constant, I can say that this is equal to 1 over n squared times variance of sum of xi's, and I goes from 1 to n. That is equal to 1 over n squared times, here we can apply the variance onto each element separately. I goes from 1 to n, and I know that the variance of x's is the same. It's not changing, and all of them is equal to p times 1 minus p by definition, right? So this is 1 over n squared times, and I have n such variances. So n times p times 1 minus p. P times 1 minus p is the variance of a single x, but I'm summing n such variances. Therefore, it should be n times p times 1 minus p. So that is going to be equal to, so n's cancel each other out. I have p times 1 minus p over n. Okay, that is the solution. So I did not go for, you see, I wrote it, but I did not go for this one because I could easily find the variance. Obviously, you can get it from by applying this formula too, but that is going to be a bit messy, I guess. It's much easier to apply the properties of variance. Okay. So here we're assuming that x's are IIT. Therefore, you can interchange the summation and variance. Okay, it's a specific case when you have IID assumption. Okay, so what else? In B part, we have to find the minimum n such that this probability is greater than 0.9. Let's think of this. So we are finding the probability that, so we have to apply another version of the Chebyshev here, probability that xn bar minus p is less than 0.1 is greater than 0.9. So let's go back and look at the Chebyshev's formula. Yeah, we have Chebyshev's formula. Now we're going to use this relationship. In this case, we're going to use the second inequality, because here we are interested in the, in the case where probability of the absolute value is less than something, right? So let me rewrite it. So probability, this is the Chebyshev's formula. So x minus mu is less than k times sigma is always less than, is always actually greater than 1 minus 1 over k square, right? So we can check it once more. So less than k sigma is greater than 1 minus 1 over k square. Okay, so here, this is the general formula, but what we see here is the 0.9 is corresponding to 1 minus 1 over k square, and k sigma corresponds to 0.1. This is basically 0.9, and k sigma corresponds to 0.1. So we can say that, 1 minus 1 over k square is equal to 0.9, and that means that 0.1 is equal to 1 over k square, which means that k square is equal to what? 10, which means that k is equal to square root of 10. Okay, nice. Now this is our k, and we said that k sigma should be equal to 0.1. So this implies that square root of 10 times the standard deviation. We know that the standard deviation of x bar is what? It's equal to square root of p times 1 minus p over n. And that thing should be equal to 0.1 by definition here, right? So k sigma is equal to 0.1. And if this is the case, then if you take square of both sides, then it's going to be equal to 10 times p 1 minus p over n is equal to 0.01. We took square root of both sides. Then it turns out that this implies that you just find n from this formula. N is equal to, so 10 over 0.01, that gives you 1000 times p times 1 minus p. So this is the solution. So n should be 10 times of the variance to have this inequality. Okay, so that is the solution for example 15.